So welcome to problem solving session for the course Linear Algebra. I'm Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 6, that is problems related to linear maps and kernel of a linear map and image space of a linear map. So let us start with our first question. Determine whether the following maps are linear. So first one, that f from R2 to R2, f of x1 comma x2 is defined as x1 square comma x2. Second one is f from R2 to R2, f of x1 comma x2 defined as x1 plus 1 comma 0. Third one, f from R square to R square again, such that f of x1 comma x1 comma x2 is x1 plus x2 comma x1. Fourth one is f from R3 to R2 such that f of x1 comma x2 is first entry is mod of x1 minus x2 comma 2x3, and fifth one is f from R3 to R2 such that f of x1 comma x2, this is f of x1 x2 and x3, x1 comma x2 comma x3 goes to 3x1 plus 2x2 comma x1 plus x3. So this is our question, and we have to check whether these are all R linear maps. So note that these R square, R3 here all are R linear spaces, R vector spaces. We know how the addition and addition and scalar multiplication of these spaces as R vector spaces is defined. So I hope you know that. And we have to check now whether these are R linear maps. So what does a linear map between vector space means? So if f, so let us first understand what linear map means first. So let K be a field and V and W be K linear vector spaces. Then F from V to W is it's called a linear map if it satisfies the following condition. First one is for all x comma y in V, f of x plus y is f of x plus f of y. So this addition here, when it is happening in V, and this addition here is happening in W. Okay. And the second property is for all a in K and for all x in V, we must have f of ax is equal to a into f of x. So this scalar multiplication here is happening in V and this is happening in W. Okay, so this is what a map being linear means if it satisfies these two conditions. So we have to check whether these two conditions are satisfied for these maps here. So before moving to that, also note that once we have this condition satisfied, one more condition we can derive from here is f of, no, that this implies f of 0 into x. So this is scalar multiplication here into 0 into f of x, right? So this anyway becomes 0, and we are now starting with the 0 itself. So it also implies that f of 0 is 0. Okay, so this 0 is here from V, and this 0 is here from W. So this is one property which we have of linear maps, is that 0 always maps to 0. So, when you are given such questions uh, to check whether a given map is R linear map or any K linear map, a given map is whether a linear map between vector spaces or not, it's always better to first check whether 0 is going to 0, because that is very uh, what we can say easy, at the same time it's very effective when we have to check whether the given map is linear or not. So yeah, uh, so that's what we will be doing here, and I will tell you why this condition, checking whether 0 going to 0, is pretty handy when we actually calculate, or when we try to determine whether the given map is linear or not. So let us start with the first map. So first map is f of x1 comma x2 goes to x1 square comma x2. Yeah. So first map is f is from R2 to R2, and it is f of x1 comma x2 is going to x1 square comma x2. Okay, that's it. That's the map. And now we have to check whether it is linear map or not. So first condition. So first we will check whether this this is just extra condition which I have. Alright. So to check whether we check whether f of 0 0 is 0 0 or not. So here what is it? F of 0 comma 0 is going to 0 square comma 0, which is indeed 0 comma 0. So first condition is satisfied. So this 0 condition is satisfied. And now we will check the first condition, that is for, so first condition. So let x1 comma x2 and y1 comma y2 be in R square. Okay, and we have to check now that f of, now addition of this, so it is x1 plus y1 comma x2 plus y2 is equal to f of x1 comma x2 plus f of y1 comma y2 or not. This is what we have to check. So let us start with the first condition then, left hand side. So this is f of x1 plus y1 comma x2 plus y2, and this is equal to x1 plus y1 whole square comma x2 plus y2. And when we like open this bracket or take the square, we get x1 square plus 2x1 y1 plus y1 square comma x2 plus y2. This is my LHS, and RHS is this f of x1 comma y1 plus f of x2 comma y2. If we want to check this, then it is then f of x1, oh sorry, this x1 comma x2 plus y1 comma y2. Yeah, so this is x1 square comma x2 plus y1 square comma y2. So this is x1 square plus y1 square comma x2 plus y2. And these two are not equal, right? The second coordinate is fine. So this one is okay. This one is okay. But this is not matching. The first coordinate is not matching here. So when x1 non-zero and y1 non-zero, this uh, In that case, if x1 and y1 both are non-zero, then this 2x1 y1 will be non-zero. Okay, and in that case, this x1 square plus y1 square, that is first coordinate of this right hand side term, will not be equal to x1 square plus 2x1 y1, sorry, plus y1 square. Okay, hence in general this this map defined here is not linear map because it does not satisfy this first property. So this is, since this is related to zero, it is called this zeroth property. Okay, so yeah, so once we have one condition is not satisfied for this map to be a linear map, we don't need to check for the second condition, because if something is a linear map, then it must satisfy both the condition. So this second condition we do not need to check. We can conclude from here itself that f is not a linear map. Therefore, f x1 comma x2, this map is not a R linear map because it does not satisfy the first condition of addition. Now the second question is, the second map which we need to check is x1 comma x2 going to x1 plus 1 comma 0. So this is again f is from R2 to R2, and f of x comma x1 comma x2 is defined as x1 plus 1 comma 0. Okay, and now as I told you before, we have these two conditions for to check whether the given map is linear map or not. And from second condition, we can derive this, that f of 0 must go to 0. And as I suggested that if you are given any map, then it's better to check with the zero condition first, whether the 0 is mapped to 0, because it's comparatively easy to check. So if if this is not holding for given map, then we can in the first step itself can reject that no, the given map is not linear map. Okay, so we want to first, let us check that uh, we have to check that f of 0 0, whether it is equal to 0 0 or not. So this 0 is from the domain and this one is from the codomain and so on. So f of 0 0 here is what? Is 0 plus 1 comma 0. So this is 1 comma 0. Okay, so this is not 0 0. So it is like, so this implies that the second condition for the linear map is not satisfied when the scalar, when a is 0. So what this a means, that for second condition what we choose, second condition is actually second condition here is that f of a x is equal to a into f of x. So when I take a is equal to 0, it must satisfy that 0 0 going to 0 0, which is not happening in this case. So that is f of a x not equal to a into f of x for a is equal to 0. Okay, so therefore this map is not, therefore f from R2 to R2 such that f of x1 comma x2 is this x1 plus 1 comma x2 is not a linear map. So note that using this 0 0 condition here, we actually saved ourselves a, some calculation, because it was easy. Eventually, if you check for the first and second condition also, this map does not satisfy any of those. But yeah, this condition you can keep in mind to check any given linear map whether it satisfies, to check to determine whether the given map is linear or not. So now the third one is f of f is again from R2 to R2, and question f of x1 comma x2 is defined as x1 plus x2 comma x1. Okay, and we have to check. So again, we will check that to check whether f of 0 comma 0, whether it is equal to 0 or 0 or not. So f of 0 comma 0 is what? It is 0 plus 0 comma 0 in this case. So it is 0 comma 0, and hence this condition is satisfied. So this one is okay. So now the first condition, that is we have to check for x1 comma x2 and y1 comma y2 in R2. We have to check that f of, when I club those, f of x1 plus y1 comma x2 plus y2, this is x1, this is just addition of these two. If I call them x and y, so this is just x plus y. Okay, not defined, I mean this is x plus y. And whether I have to check whether this is equal to x1 comma x2 plus y1 comma y2, f of y1 comma y2. So let us start with the left hand side, that is f of x1 plus x y1 comma x2 plus y2. So as per the definition, it is addition of x1 x2. So first and second coordinate, and then third one, second coordinate is the first one. So it is x1 plus y1 plus x2 plus y2 comma x1 plus y1. Okay, and this is equal to x1 plus x2 plus y1 plus y2 . Yeah, x1 plus x2 plus y1 plus y2 comma x1 plus y1. And if I separate those, I will get this x1 plus x2 comma x1 plus this is y1 plus y2 comma y1, and this is my f of x1 comma x2, and this is my f of y1 comma y2, and this is exactly what I wanted. Okay, so first condition is satisfied by this map about the of addition. So let us go to the second condition, that is we have to check for all A in R. Since we have to check whether this is R linear map, my scalar must be from R, and this x1 comma x2, let it be element from R2. Then we have to check whether f of a x1 x2, so this is a x1 comma a x2, whether this is equal to f of a into f of x1 comma x2. Okay, and this is a into x1 comma x2. Okay, so again we are starting with LHS, that is f of a x1 comma a x2. This is equal to what? A x1 plus x2 comma a x1 from the definition of the map, which, so I can take a common from this, x1 plus x2 comma a x1, and if I take a common, I get this, and this is nothing but f of x1 comma x2, if you notice. So therefore all these three conditions are satisfied. So the zero condition is satisfied here, the addition is satisfied, and the scalar multiplication is also satisfied. Okay, so therefore this map here is linear map. Therefore, f from R2 to R2 such that f of x1 comma x2 is equal to x1 plus x2 comma x1 is a linear map, is a R linear map, okay? And now let us check for the fourth one. F is from R3 to R2 now. And we have to check that f of x1 comma x2 comma x3, this map given like this, x1 minus x2, this is the real mod of number. So this is this normal modulus of a real number. Yeah, so we again will check for this zero condition. So that is to check whether f of 0 comma 0 is 0 0 or not. So this is f of 0 comma 0 comma 0. So here we are working with R3. So 0 0 is in R3. Yes. And this is equal to mod of 0 minus 0 comma 0. So this is anyway mod of 0, which is, let me just write. So this is 0 comma 0. So that is satisfied. So that's not, so we are okay. So now the second condition we have to check. So the first condition, that is to check for all x1, x2, x3 and y1, y2, y3 in R3 whether f of x1 plus y1, x2 plus y2, x3 plus y3 and this is just addition of this. We have to check this condition. So let us start with LHS. So LHS is this is equal to f of mod of x1 plus y1, yes, minus x2 plus y2, so not comma 2 x3 plus y3. So this is plus y1 minus y2 modulus of the mod of this comma 2x3 plus 2y3, and that's it. We can't separate this further because this is not true in general. This mod of x plus y is equal to mod x plus mod y. This is okay. So now let us see what is RHS. This is mod of x1 plus x2 comma 2x3 plus mod of y1 plus y2 comma 2y3 So this is my f of x1, x2, x3 plus f of y1, y2, y3 is. And in general, as I said, that since this condition is not true, this does not hold in general, these two are not equal. So LHS is not equal to RHS in general, as this. This is not equal to this mod of x1 minus x2 plus mod of y1 minus y2. And if this one is difficult to visualize, you can check particular xy and you can try to calculate this. And yes, and you will see that that's not true in general. And when take any two numbers and this would hold. And secondly, so second condition, so this, for example, if we take x1, x2, x3 as 1, 2, 3 and 4, 5, 6, then f of 1, 2, 3 will be what? It is mod of 1 minus 2, comma 2 into 3, and this is 1, comma 6, and f of 4, 5, 6 is mod of 4 minus 5, comma 2 into 6, that is 1, comma 12. And when we take addition of this, so it will be f of 5, 7, 9, and it is, right, 5, 7, 9, yes. It is mod of 5 minus 7, comma 2 into 9. That is, okay, it is holding in this case. Let us see. $18, right? Did we choose wrong numbers here? Subtraction. Let us take minus. Maybe that would help. Minus and minus 6. Then it will be mod of minus 4 minus minus 5 and minus 6. So this will be again 1, comma minus 12. And here it will be 1 minus 4 is minus 3, minus 3 again, right? Yeah, and again minus 3. So this is mod of minus 3 minus 3 minus minus 3. I hope I'm correct here. Yes. Comma 2 into minus 3. And that is equal to, this is plus minus. So this is 0, comma minus 6. So yeah, so f of 1, 2, 3 plus f of minus 4 minus 5 minus 6 minus is addition of these two. So that is 2, comma 6, 2, comma minus 6, but f of addition of these two. So addition of these two equals minus 3 minus 3 minus 3. This is 0, comma minus 6. So these two are not equal. So I hope it is understood that this does not hold in general. Okay. And though we checked for the addition and we also saw the explicit example, understanding this one through scalar multiplication is pretty easier to observe. For example, if we want to check this same map, so let this A be in R, and again this x1, x2, x3 in R3. Then and I want to check that whether for this, whether my f of ax1, ax2, I hope you know that this is a scalar multiplied. So this is my ax, and I have to check whether this is equal to f of x1, x2, x3 or not. And you can check that when I look at the image set. So what is this? F is mod of this ax1, comma x2, comma 2x3. So note that whatever my x1, x2 are, the first coordinate, this first coordinate is always greater than equal to 0 for all x1, x2, x3 in R3. Can you see that? Always positive, but in general, if I take, so this is what, if I'm correct, so this is mod of A into mod of x1 minus x2, comma 2 x3. And f of, now the left hand side, this a f of a x1, sorry, x1, x2, x3. This is equal to a into this mod of x1, comma x2. So this is ax3. That is okay. That's not a problem here. x1, comma x2, comma x3. And here this is just a into mod x1, comma x2, comma this is 2x3. 2a into 2x3. That is okay. But the thing is, this could be negative. So if this is always greater than equal to 0, as we saw here. Okay. But if my here, if I choose a in R2, so in R such that a is less than 0, then this first coordinate becomes 0. So then this a into mod x1, comma x2, this becomes less than 0 because this is anyway greater than equal to 0. So this is non-negative. And if I multiply it by, so if I assume that this is strictly positive, and if I multiply this by some negative number, then the product will be negative. But the first coordinate of this scalar multiple, so this LHS, is always some non-negative integer. So to check that, so for example, this f of 1, 2, 3, which we calculated, if I, so that was what? This was 1, comma 6, if you remember. And if I take my a to be minus 1, then this a into f of 1, 2, 3 will be what? Will be just minus 1, comma minus 6, right? But this f of minus of this, so f of minus 1, minus 2, minus 3 will be mod of minus 1, minus 2, that is okay. Mod of minus 1, comma minus 2, sorry, minus or plus. It is minus or plus. Does not matter in both the cases. It is plus, I think. Oh, it is minus. Whatever the case. In both the cases, comma 2 into minus 3. So this is 1, comma minus 6. So these two are not equal. You can see that these two are not equal. This is not equal to minus 1, comma minus 6. Okay. So therefore, this map is not a linear map. Okay, so therefore, hence f from R3 to R2 such that is not a linear map. I hope this is okay.
Can you just explain once more, please? Why
This
is
one, the
yeah,
negative.
yeah.
So, because the conditions which a linear map must satisfy are not satisfied here. So not so this modulus part, right? I mean, I mean, this is what I think you must have some doubt in, right?
Yeah, I mean, initially you said it must be greater than 0, equal to 0. And then here you said if A belongs to R, then A must be less than 0. Then A multiplication of x1 minus x2 should be less than 0. But in above, we are telling that it should be greater than equal to 0.
Exactly. So that's the contradiction that this won't hold. That's why this map is not linear map because that's not happening. So so we have to check whether these two are equal, right? What we have to check whether A into F is equal to F of AX or not, right? This is my condition for a map to be linear, right? And
Okay,
yes, and these two are exactly that. So this is my F of AX and this is my AF of X.
right.
So if the linear condition is satisfied, then this should be satisfied, right? I mean, this something like this should not have happened. They must be equal always. But that's exactly what is happening. When I'm taking F of AX1, AX2, AX3, the way F is defined. So the way F is defined, this first coordinate will always be 0, always be greater than equal to 0, if you see. Because first one is what? It is modulus of some number.
Modulus will always be positive, yes.
Yes, non-negative. So this will always be 0. So f of ax1, when I have here, this is whatever, this is what. So in this case, it is some, these two like a comma b. It will be some, not a comma b, let us take c comma d. C will always be non-negative, the way f is defined. Because in the first coordinate, it is non-zero for this f, okay, for this f here,
Okay.
okay. But if I take non-zero, so what I have here is now, this is non-zero term, right? And but if I take a negative, then
Hmm.
this becomes less than equal to
It,
0.
it will
That's
become
what happens.
okay.
Yes, right. Because this in the so the for f, the first coordinate is non-negative. That's there. But the moment I multiply it by negative scalar, because when I say that f is linear, it should satisfy for any scalar. But here, if I take a negative, the first coordinate becomes non-positive. If
Okay.
the 0, then it will be less than 0. And if I choose this to be non-zero, then it will be something like this, to be technically correct.
Okay.
Okay. And if this is strictly non-zero, then this is something positive and then multiply. That's exactly what is happening. When I am taking f of minus of something here, this was my f. This is if this is equal to f of minus 1 into 1 to 3, right? My a is minus 1 here.
Right. Right.
So here f is non-negative if you see.
Here F is
Yes, non-negative because does not matter whatever the coefficients here are. Does not matter whatever the numbers I take here. This first coordinate is always non-negative. But since a was negative here, when I multiply it from outside in W means in my codomain, then the first coordinate becomes non-zero or negative, which is
negative.
not there. And that's the contradiction we are getting to conclude that f is not a linear map. Is that okay?
Um,
So the point is the way f is defined, f of the first coordinate always be non-negative.
yeah,
Doesn't
I
matter
mean,
whatever scalar multiply you multiply here.
when a scalar is already multiplied with the x1, x2, the value may become positive, but when the scalar is totally outside, it may become
Yes,
negative
yes,
also.
yes, yes. When the scalar is multiplied in domain, the
Hmm.
resultant is non-negative always. But when I'm taking the condition in the codomain part, this is happening in R2 and this is happening in R3.
Acha,
Okay,
acha.
so
Okay.
yes, this is in R2, right? This is in codomain. This, right? This is in R2 and this is in R3.
Acha, acha. Okay.
So as I said in the beginning that when we check this, f of ax is equal to a f of x, this scalar multiplication is happening in, so if my f is from V to W, this scalar multiplication is happening in V, right? This is f of some element in V, right? So this multiplication is in V, but this multiplication here is in W. So the way we are, the multiplication is defined in both the both the vector spaces is different, and that's why this is happening. So this is like I'm multiplying first in my codomain and then taking its image, and here I have image of some element and then I'm multiplying it by some scalar in the codomain. So, and when they both coincide, that's when I called my map as a linear map, and that's exactly is not happening here. When I'm
Okay,
multiplying it here, the image is non-negative, but in the codomain, when I multiply by some non-negative real number,
understood, understood.
yes. Okay. So yeah, even in earlier, if you in when I define, see, I explicitly wrote in both the condition that where the addition is happening and where the scalar multiplication is happening.
Actually, I
So
joined late, got
yeah,
stuck in
yeah,
the topic.
yes,
Right.
that's
I
okay.
understood the concept, yeah, from R3 to R.
Yes. Yeah. And secondly, I since you were not there, I was just added this, that when you have to check whether a given map is linear or not, it's easier if you check this condition first, whether 0 is going to 0 or not. It comes handy in many cases like this, which we discussed in second part here. Because see, if you can start with addition and scalar multiplication, and eventually you will arrive at those conditions that those won't satisfy. But this is quick way to check whether given map is linear or not. If you want to discard that it is not a linear map, if it's linear map, you have to check all the conditions that's there. But yes, that just kind of hint. And next map is similar kind of map, but different. So fifth one is f from R3 to R2 again. And this f of x1, comma x2, comma x3 is defined as 3x1 plus 2x2, comma x1 plus x3. Okay, and this zero condition we check that whether f of 0, comma 0, comma 0 is equal to 0, comma 0 or not. So what is this actually? This is f of 0, comma x1, comma x2, comma x3. I have to check whether this is equal to 0 of f of x1, comma x2, comma x3 or not. But whatever this term is, this will be something in R3. So this is, we have to check this. Okay, so I hope, yeah. So let us start with this, that LHS is f of 0, comma 0, comma 0. And then this is, sorry, this is equal to 0, 3 into 0 plus 2 into 0, comma 0 plus 0. So this is anyway 0, comma 0. And that's exactly what my, if I take this is anyway 0. So I don't need to. So this is equal to RHS. Because 0 into whatever term here is, this is anyway equal to 0, comma 0 in R2. Is this okay? I mean, you understood what this is here.
So, but
This,
for
yeah.
all zero, it will be always true, and because whether it you multiply inside the domain or codomain, the resultant will be zero always.
Um,
It not be.
Sorry, sir. Could you please repeat again?
I mean, if you take for zero value, it will
Mm-hmm.
always hold true because whether you multiply in R3 or in R2,
It
I
will
mean,
always be R2
is zero.
because this is happening because this is a linear map. For example, if when we did that for the second map, which we wanted to check here, whether f of 0, 0 is 0, 0 or not, it was not the case because f of 0, comma 0 was becoming 0 plus 1 because the map is defined like this, x
Acha,
plus 1, comma
so
0.
okay, okay.
So yeah,
That
so in
is
that case,
clear,
we
huh?
got this
Point
1,
being
comma
not
0. Yes. So
clear.
here that happened because everything is good. Okay, we will see that this map is actually linear map. That's why that good condition is happening. But in general, the way the map is defined, that need not hold always. Something like this can arrive. That's why I check 0, 0 happens or not.
Mm-hmm.
Even in this map, you could have start with addition and scalar multiplication, and then you would have got maybe x1 plus x2 plus 2, which is not equal to x1 plus x2 plus 1. This is in domain and this is in codomain and so on. And eventually you will get that this is not linear. But this 0, 0 condition actually helped us. It just saved us our time, nothing else. You can just ignore this. This is actually particular case of the scalar multiplication, because we know that f of ax must be equal to a into f of x. So I am just taking this particular a is equal to 0 because it's easier to get rid of unnecessary terms there.
Okay.
That's it. Yeah. I mean, even if you don't check this 0 condition, it's completely fine, but it helps sometimes. That's it. So yeah, we were discussing that let me just yeah, so we were checking this. Uh, sorry, but yeah. So yeah, we have to check this x1 plus x1 plus y2, so y1, x2 plus y2, comma x3 plus y3, whether this is equal to f of x1, comma x2, comma x3 plus f of y1 plus y2 plus y3, y1, comma y2 plus y2, comma y3. Yeah. So let us start with the LHS. I hope I'm there. I'm still there. Yeah. So yeah, f of x1 plus y1, comma x2 plus y2, comma x3 plus y3. This is equal to f of, this is equal to, from the definition, it is 3x1 plus 2x2. So 3x1 plus y1 plus 2x2 plus y2, comma x1 plus y1 plus x3 plus y3. Sorry. This is 3x1 plus 3y1 plus 2x2 plus 2y2, comma x1 plus y1 plus x3 plus y3. And since addition is commutative, we can just club this x terms and y terms together, plus 3y1 plus 2y2 here, and here also x1 plus x3 plus y1 plus y3. And this gives me this 3x1 plus 2x2 here, or x3. Yeah, it's x2. Yeah. Comma x1 plus x3 plus 3y1. So I'm just separating these additions here. y1 plus 2y2, comma y1 plus y3.
Can you explain this
So
step,
this is,
this last step?
yes, I'm just separating this addition. So this is a comma b plus, sorry, a plus b, comma this is c plus d. So I'm just separating them as a comma c plus b comma d. Just this and this I'm clubbing together to get this, and this and this to get this. Or maybe these two I'm taking here, and this one
Okay.
I'm taking here. That's it. x1 plus x3. So all the x clubbed together, all the y clubbed together. So this is precisely what is happening here. And then this is my, if you check, this is f of x1, comma x2, comma x3. And this is f of y1, comma y2, comma y3. Is this okay?
You're fine. But above
Yeah.
clubbing is with which rule it is? The clubbing, I mean,
So
clubbing all x.
this is just addition in real numbers, right? These are all real numbers here. These are all real numbers. This is all happening in R.
All that is fine. I am just saying uh, uh, the value which is before comma and after comma, this A and C, with which rule we have clubbed together.
This is just definition, how we defined addition in R2, right? I mean, we define addition in R2 like this. A comma B plus A comma, yeah, A comma C plus B comma D is equal to A plus B comma A plus C comma B plus D, A plus B comma C plus D, right? And so if I have this, I can also do this. So this is there, right? I mean, we can always do this.
Okay.
For example, if I have 1 comma 1 plus 2 comma 3 plus 5, I mean, this is also equal to, I mean, this I can also do it
Yeah,
like
yeah.
this, A
Okay,
comma D
understood.
plus B comma C. But I want to show that this is exactly what I want. I mean, if you don't want to separate them like this, you can just leave it here. You
Understood,
can just leave
understood.
it
I mean,
here.
component wise, it
Yeah.
is addition.
Yes. Or if you, I mean, let's just do that also. If I
Bit
take
clear now, not
RHS,
clear. I got it, yeah.
yeah, okay. Because ultimately, when you start with this, I mean, this is my RHS, right? And when you start with
Mhm.
this and then start separating them from, I mean, going from down to up here,
Hmm.
I will get this, right? And then this is precisely what I'm adding them actually. And this is what is these terms are here. Or there are extra brackets which are confusing maybe. Is this okay?
Yeah, that's fine. That's fine.
Yeah. Uh, yes. So the next, I don't know, but why it ended in the first place, but okay. Yes, so let us do some next, let's do next question. Question 2, that let F1 from V to V1 and F2 from V to V2 be,
Which question it is?
this is 6.5 of assignment sheet. Yeah.
Okay.
The homomorphisms of K vector spaces. So homomorphism of K vector spaces means that it is linear map, K linear map. Okay, and further we have,
This is
let,
6.5, huh?
yes, 6.5. There are different, so it's not T 6.5, it is 6.5. It is on page number 4
Ah, I got it,
on
got
the
it.
last page.
Okay.
Yeah. Further we have this F from V to V1 cross V2. This be the K linear map, and it is defined by f of x is equal to f of x1, f1 of x, comma f2 of x. Okay, we have to show that F is an isomorphism if and only if F1 is surjective and the rex the res the restriction F2 at kernel of F1. Yeah, that is, this is map from kernel of F1 to FV2 is bijective. So there are so many things going on in this question. So what we have is we have these two maps, F1 and F2, and F1 and F2, and just let me check. Yeah. F1 and F2 are from V2, V1 and V2, V2 respectively. And the map is defined like this. So F is from V to V1, F1 is from there, F2 is from V to V2. And we have this new map from V2, F of V2, V1 cross V2, such that this X is going to F of X, F1 of X, comma F2 of X. Okay, and we have to check that we are given that this map is in isomorphism. So isomorphism means, so let K be a field, or let V and W be K vector spaces. And we say that F from V to W is an isomorphism if F is linear map and F is bijective. Okay, these two conditions must satisfy. So what they are saying is that this F map, the way they have defined here, is it's isomorphism. That is, it's both. So bijective, I hope you know, bijective means injective plus surjective. And yeah, so this condition means that F is an isomorphism if and only if F1 is surjective and the restriction map is bijective. So instead of now checking, I mean, this map here. So if you see, here we are talking about F completely, but to declare that F is isomorphism, I'm just taking these two maps. That F1 is surjective. I don't even want to check whether F1 is injective or not. F1 is just surjective. And second condition, this one map, F2 map, on the kernel of F1 is bijective. These are the only conditions we need to check. And that's it. So this is what we have to prove now. Is the question okay?
Can you repeat this last line?
Yeah, so what I was saying is that, oh, sorry. We are given that F is isomorphism. We have to prove that F is isomorphism. So when I say that F is isomorphism, what I need to check? That F is linear map and F is both injective and surjective. And this theorem or this result is saying that in order to prove that F is isomorphism, or in order to declare that F is isomorphism, I only need to check that F1 is surjective and that this F2 map is bijection on the kernel of F1. So we are not actually checking that F is injective, surjective, and those properties. Instead, we are saying that F is isomorphism if these two conditions are satisfied. So we are trying to uh, give criteria of bijection or isomorphism of F using the properties of F1 and F2. Okay, so in this case, they are saying that it will be, so if you observe that, we do not even need F to be bijective in order to have F as isomorphism. F1 being surjective is enough for us. Also, in for F2 case, we only have to check whether it is bijection on the kernel of F1. This is subset of V actually. So if it, so these are pretty restrictive conditions compared to what exactly we need to declare that F is an isomorphism. Is that okay?
Yes.
Yeah. So let us try to prove the first part, that I have if F is an isomorphism. So for first part, F is an isomorphism, and to prove that F1 is surjective, two conditions we need to prove. F1 is surjective, and second condition I need to prove is that this F2 restricted to kernel of F1, that is this map, is bijective. These two conditions I need to check. So F1 is surjective. So let us start with the proof that
Why is F1 need not to be checked for bijective? Why only F2 is need to be checked for bijective?
F2, I mean, it's F2, we are not even checking whether entire F2 is bijective. We are saying that it is bijective only on the kernel of F1. And I mean, that is the theorem we need to prove. So the injectivity, or I mean, see, F1 is entirely different function. F1 is from V to V1. F is from V to V1 cross V2. F1 is from V to V1. So F1 being bijective is not or isomorphism does not really help to declare this is
Um,
isomorphism, because I can very well define maps such that even though F1 is uh, isomorphism, F need not be isomorphism, right? For example, if I take F from V to V1 cross V2 such that my F1 is just V going to V, suppose my V1 is V, and my F2 is just image map, and my F2 is V going to 0. So even though this, is this helping? Let us see. Even though this map, let us check V1 cross V2, V cross V, let us say.
Here in
So
this
this will be
question,
working. Yes, this is actually happening. Uh,
there's a little fundamental doubt because in above you mentioned if it is isomorphism, then F should be linear and F should be bijective. Uh,
yes,
this you said if F need to be isomorphism, then we have to show that F is linear and F is bijective. But in this given question, there are two functions, F1 and F2. And then there's a
mm-hmm.
third function called F, which is from V to V1 cross V2. And we need to show that
Yes,
F is isomorphism. So
yes,
if we go by definition, then we have to show that F is isomorphism if and only if it is F is a linear map and F is bijective.
yes. So that we will do in the converse part. So using these two conditions, we will prove that F is isomorphism. And to check that, we will show that it is linear and bijective. For now,
Okay, but
our
here
given information is F is isomorphism. And using that, we have to prove these two conditions. So it is given that F is isomorphism. We don't have to check whether F is isomorphism or not, at least for this part. And for the
okay, it is
converse
given.
part, we have to check. Yes, it is given that F is isomorphism and these two conditions are satisfied. We have to prove that these two conditions satisfy in this case. And for converse part, to check that F is isomorphism, I will actually be proving that it is injective, it is surjective, and it is linear map. That's there because that's how we have defined. So F is linear, so we do not need to check. Uh, we can check that as well, but we don't need that. Yes, we will be actually proving that it is linear, injective, and surjective in order to check the converse part. But for now, we are given that F is in isomorphism. It is, we will be using those conditions that it is injective, surjective, and linear map to prove this. Okay?
Okay. Okay.
Yeah. So let us start with the surjectivity of F1. So first one, that F1 is surjective. So to show that F1 is surjective. So F1 is surjective means F1 is what? F1 is from V to V1, right? And we have to show that it is surjective means for all V1 in V1, there exists some V in V such that this F of V is equal to V1, right? This is what we want to check. But note that for this V1 in V, this V1 comma 0 belongs to V1 cross V2, right? And then, but since F from V to V1 cross V2 is an isomorphism, there exists some V comma W in, sorry, there exists some V in V such that F of V is equal to V1 comma 0, right? Or let us take X if you don't want this to be coinciding with, sorry, V1 comma 0. Is this okay so far? There exists some X such that F of X is V1 comma 0. So if that is the case, this implies that F of X is equal to F1 of X comma F2 of X. We don't care what F2 of X is here. Is V comma 0. That is F1 of X is V. 1. Right? So therefore we choose this V to be X and we got that F of this V is now V1. So therefore for all V1 in V1, this capital V1, there exists X or V in V such that we got that F of V is actually V1, small v. Is this okay? So using the isomorphism of F here, we obtain this element V or X, whatever you want to call, such that this F of V is V1. Is that okay?
Can you just go a little above? Where did you take this V1 comma 0 for this, from where the 0 came here?
See, we
V1
have to
comma
make
0.
use of, yeah, we have to make use of uh, this. map F, right? F is what? F is from V to V1 cross V2. And it is such that F of V is F1 of V, comma F2 of V. So if I want to make use of F1 here, something, then I mean you can also take any V2 here, does not matter. I mean you do not need to
Okay.
take 0 always.
Acha, acha,
You can
okay,
take
okay.
any. Yes,
Anyway, we are
yes.
coming with the F1x is equal to V1. Okay.
Yes,
We are
yes,
just
yes.
fine.
Yes, I only need to check here. Even if you take V1 comma V2 here, suppose sum, then
Anything
this
you
will
take it.
be, yes, it does not matter because for this V1, V2 also, uh,
Hmm.
there will be some x such that this f of x will be V1 comma V2. And again,
Hmm.
I don't care what this V2 is or f of V2 is. I only need to check whether this f1 of x is V1 or not. You can definitely
Hmm.
check, take any V2 here. It does not matter. 0 because it's easy to I mean, because it's always there.
Okay. Fine.
Yeah, yes. And yes, so that's it. We just proved that. So therefore, F1 is surjective map because for every element, I just got that it is surjective. Sorry, yeah. For every element, I could find the pre-image. Yes, you have any doubt? Okay, okay. Yes, that's it. And yeah, further, I was saying that it. Yeah, first part is done. Now we have to check the second part. That F2 restricted to this, that is, we have to check that this F2 restricted to kernel of F1 such that kernel of F1 going to V2 is bijective. Now I have to check that this map is both injective and surjective. Okay. Okay. So let us check the surjectivity part. Bijective means injective plus surjective. So let us check surjective part first. So for surjective, we have to start with some element here and then show that there exists some element in kernel F1. So let V2 belongs to this capital V2. And now I'm considering, so now I have to make use of F again. So I will take this 0 comma V2 here in V1 cross V2. Again, as I said, you can take any element here, does not matter. You can take anything here. V1 also would be okay. But yeah, so for this V2, we have this element here. And again, since F is surjective, F is an isomorphism, there exists some V in V such that this F of V is 0 comma V2. So, but this is what? This is F1 of V, comma F2 of V. So this imply that, sorry, F1 of V is 0 and F2 of V is V2. Right? So this imply what? That V belongs to kernel. Since F1 of V is 0, here in this case, we can't take any V1 here, okay? Because we want to show that the element which we want belongs to kernel of F1. So that's why we are taking 0 here. So here, let me just write this in some. Here we must take 0 comma V2 instead of any v1 comma v2, as we needed to show that this v belongs to kernel f1, because now this map, now this is in kernel f1 and not in v. This is properly contained in v. So if you take any element v1 here, then we can show that there exists some v such that f2 of v is v2, but that v will be in my space v. But I want it to be in kernel f1. That is that is subset of my original space v. So to have this condition, this v will belong to kernel f1 and f2 of v is v2. So therefore f2 from f2 restricted to kernel such that is surjective, because we could find this v in my set kernel f1 because I'm taking 0 in the first coordinate. Is this okay?
Okay.
Yeah. So second part now, now I need to check the injectivity. So to check injective map, I hope you understand. To check something is injective, what we can do is the the traditional definition of injective is if f of x1 is not equal to f of x2, then this implies that x1 is not equal to x2. This is my traditional definition of uh, what we say. Is this true? F of x1? Yeah, this is my injective condition. But in case of linear maps, we have, if you check, it is okay. We say that f is injective in homomorphisms. F is injective. We have this condition if and only if kernel of f is just 0 set. This is there, and we will be using this condition. I don't know exact. In the lecture also, I think this will be this has been proved. If not, then prove this that f is injective if and only if kernel of f is 0. Okay. I hope this is.
So that is the reason we took 0, because kernel of f is 0 always. That's why we took the above 0 and v 2.
No. Kernel of f is not always 0. Kernel of f is 0, that is okay, but we are not actually using the injectivity of f here.
But
Yes,
since
in this
that
case,
condition said the f2 at kernel f1, that's why we took 0 here. No? That is the reason.
that is still only using the surjectivity of f and not the injectivity of f. We have not yet dealt with
No, that is okay. But
injectivity of.
0 means
Yes.
because of the kernel f1. No? Because f that 0 value you
Yes,
said, because if we have to take 0 v2, not v1 v2, because the kernel f1 is equal to 0 always. That's why we took 0.
no. Kernel f1 is not always 0. What is kernel f1? Kernel f1 is collection of all those v in f such that f of v is 0. We are not saying that kernel of f1 is 0. I still know that. We do not know. We do not know whether f1 is injective.
Acha, acha, okay. We are taking here
Okay.
from subjective point of view. Okay.
Yes. Here also this there exists v such that f of v is to here we are using surjectivity of f and not the injectivity. And in order to, because if that is the case, then this map is like from 0 to something, which is not true. I mean it could be true, but we don't know that. We are
Acha,
only
okay.
talking about subjectivity. Yes. And in order to, the only reason we took 0 here, because whatever v we are getting here, I want this v to be in kernel of f1. That's why I chose 0 here. Here, if I had taken some v1 comma v2, then whatever v we are taking, this f of v such that f of v will be v1 comma v2. But that v, I don't know whether it's in kernel or not, because this is what?
Maybe
This means
beyond,
f1 of,
outside the kernel.
yes, yes, because this means f of v is equal to v1. And that does not imply that, that does not make sense that v belongs to kernel f1. I want
Oh,
something
okay.
from the kernel of f1. That's why I chose v1 to be 0 here.
Okay.
Yeah. Is this okay? So injectivity, this statement is there, and we will make use of that. So suppose what I want to check that f is injective. So I need to prove that f is injective. We will prove that is kernel of f is 0. So what we do, suppose y belong to kernel of f. Right? Then this implies that f of y is 0 comma 0, right? So this implies that f1 of y is 0 and f2 of y is 0. This implies that this implies that y belongs to kernel f1 and f2 of y is 0. Right? This is f1 of y comma f2 of y. But this is equal to 0. Or let me write this. Let's suppose y belong to kernel f. So this implies that f of y is 0. But what is f of y? This is f1 of y comma f2 of y. And this implies f1 of y is 0, f2 of y is 0, and then kernel f and f2 of y is 0. Right? But since f is injective, f is an isomorphism, therefore f is injective, this implies y is 0. Is there any confusion here? See, we wanted to prove that. Oh, sorry, we don't want to prove this. We have to prove that f restricted to, sorry, f2 restricted to kernel f1 is injective. Okay. So what we have to do is we have to take, sorry.
We are going to
So
prove
suppose,
F2 is injective, ma'am.
Yes, F2 is injective. Exactly. I messed up here. Sorry.
Yes.
Yeah. So suppose that Y belongs to kernel F1 and Y uh, F2 of Y is 0. Suppose we have this. So since this is there, right, because our domain is kernel F1 and this, and we have to show that this Y is 0 now. I have to prove that this is 0. That is kernel of this F2 restricted to kernel F1 is 0. So suppose Y belong to kernel F1 such that f of y is 0. And now to show that, we have to show that this y is indeed 0. That's what we have to show. But since y belongs to kernel F, this implies that f1 of y is 0, right? Y belongs to kernel F1. This implies f1 of y is 0. And we are already given that f2 of y is 0. I hope you know how to prove that something is, I mean, if I have to say that W is injective, then what I do is let W in W, sorry, V in V, such that f of V is 0. Then we show this V is 0. That is that kernel of V is 0. Because when I start with V in V such that f of V is 0, that implies that V, I'm assuming it to be in kernel. But then I show that if that V is 0, then the kernel becomes 0 always. If F is F is injective. So that's what we are doing. We are starting with some element from the kernel of this map F2. And so what I'm doing is that let Y belongs to kernel of this. This imply that Y belongs to kernel F1 such that F2 of Y is 0. And we have to show that this Y is 0 now. But since Y is in kernel F1, these imply that F1 Y is 0. And we anyway have F2 of Y is 0. So therefore, F of Y, that is F1 of Y comma F2 of Y, is 0 comma 0. But now F is an isomorphism, and therefore injective map. This implies that Y belongs to kernel of F, right? But since F is an isomorphism, that is F is an injective map, this gives me that Y is equal to 0 since F is injective. So if that is the case, then this implies that the Y which we started here, this implies that kernel of F restricted to kernel F1 is 0 because that's where my Y was. So any Y I start from here, Y in kernel of F2 restricted to kernel F1, I get that Y is 0. So that's why, because see, 0 always belong to kernel of any map. Okay, so if I want to show that kernel of F is a 0 set, then what I need to do is, so this implies what? That this implies 0 is always a subset of kernel F. So when I did, what I wrote here is So now what I do is I start with the map from start with some element from kernel, and I show that V is 0. That is, V belongs to the singleton set, and that's what I do here. Okay, so this is pretty basic, but yeah, that's what I did here. I started with some element in kernel and showed that it is 0. So therefore, kernel has to be 0 because 0 is anyway inside the kernel. Is this okay? Sorry for the confusion earlier. I started proving that f is injective, and that was not even correct, what I wrote. But so far, is this okay that f2 is injective? Okay. If there's still confusion, please ask. So this is just first part. So therefore, f2 restricted to this kernel f1 is bijective. And so far, even after doing all this, we have still not used that f1 is injective because we don't need that in the first place. But yeah. And apart from that, now the converse part. Now the converse part. We are now given that first that f1 is surjective, and secondly we are given that f2 restricted to kernel f1 is bijective. And now I have to show that f is isomorphism. And now to show that f is isomorphism, I will actually prove those two conditions, that it is injective, it is surjective. So let us first start with the injective. F is linear map, that is there. The way f is defined, it is linear map. Okay. So kernel of f is what? It is all those v in V such that f of V is 0, 0. I'm just simplifying this. That is all those v in V such that f of V, sorry, this f1, f2 is 0, 0. Just the definition. That is all those v in V such that f1 of 0. So this is implied that if that this is happening, this implies that I can take this v in V such that V in kernel f1 and f2 of V is 0. And if that, and since this is happening, I can just take V belongs to kernel of f1 such that f2 of V is 0. And what is this? This implies that kernel of f is kernel of f restricted to f2 restricted to kernel f1. Is this okay? Okay, so but we know that, but f2 restricted to kernel f1 is bijective, therefore injective. Hence, therefore, kernel of this f2 restricted to kernel f1 is just 0, and therefore we get that kernel of f at 0. Is this okay? In general, this kernel of F is actually kernel of F1 intersection kernel of F2. If you check, let me write this properly. Because what I want, both of the coordinates to be 0 here. F1 V also 0, F2 V also 0. And when I write this kernel of F2 restricted to kernel F1, I'm anyway choosing elements from F1. And from those F1, I'm choosing elements where F2 is also 0. So when I choose element from this set here, it is actually I'm choosing elements from both kernel of F1 and kernel of F2. I hope you understand I hope it's clear what I'm just trying to say here. This is precisely kernel of F1 intersection kernel of F2. Because I'm starting with elements from F1, which are also there in kernel of F2. Okay. And this, you can just try to understand this here. And yeah. So therefore F is injective. And now the surjective part. Second is surjective. Hello? Hello?
Hello.
So yeah, surjective part here. Now let v1 comma v2 be in v1 cross v2, and we have to find an element such that f of v is, so we have to find v in v such that f of v is v1 comma v2. Okay, but we are given that f1 is surjective. Okay, so since f1 is surjective, there exists some v in v such that f1 of v is v1, right? This v1 here is in, let me just shift it. Since f1 is surjective and v1 belongs to this capital V1, there exists some v in v such that f1 of v is equal to v1. Is this okay? We are using surjectivity of f. Yes. And now we have to see that this now let now let now this f of v is what? v1 comma f2 of v, right? Uh, yeah, f2 of v. And now we need to adjust this. So now we need to adjust this f2 of v such that we get v2 in second coordinate. Right? This is what we want to do. But yeah. So note that since this f2 restricted to kernel f1 is bijective and hence surjective, there exists some y in kernel f1 such that f2 of y is,
Ma'am, one small doubt, madam.
yes sir,
Here now f of v equal to v1 comma f2 of v, right, ma'am?
yes sir, yes sir.
But actually here f1 of v comma v2 is
Yeah, we are not yet done.
because yes,
For
ma'am.
this we
Because
won't help us. We just obtain this v which is taking
mm,
care of v1 now, and we
okay,
have to add, subtract or do something to this v now such that we
okay,
can,
madam.
or if you, let us take x here. Okay, and v will be our original element which will give us. So this x is such that f1 of x is v1.
Okay, madam.
And now we still have to do something with this x such that I also get that this second term as v2. That's what I wrote here. That we need to adjust this
Okay,
f2 x such that we get v2 in the second coordinate. And to
okay,
do
madam.
that, we know that f2, yes. Uh, and to do that, f2 restricted to kernel is bijective map given. So it's surjective. So we will make use of that. So since So this f2 of x is in v2, right? So there exists some y in, note that this f2 from f2 restricted to kernel f1 is from kernel f1 to v2. So therefore, and is surjective. So therefore, for this f2x in v2, there exists some y in kernel f1 such that f2 of y is my f2x. Or I can take, see, this is f2 of x here. Wait. Is surjective. Then note that this, therefore, for f2 of x minus v2 in v2, there exists. This is pretty constructive because we have to. This v2 is small v2. This is my capital vector space v2. There exists some y in kernel f1 such that f2 of this y is this f2 of x minus v2. Is this okay so far? So instead of just taking f2 of x and v2, what I did was This is still, see, f2 of x is in v2 and v2, this small is anyway in v2. Therefore, this f2 of x minus v2 is in v2. So, and this is some new element. And for this element in my v2, there exists some y in kernel f, because now I'm talking about surjectivity of this map. So for this element, there exists some element y here such that f2 of y is this. Okay, and now we take, so now let my v to be this x minus y. So x was this, such that f1 of x is v1 and y is this. Such that f2 of x is v2. So fe is x minus y, I'm setting there. And now this, let us check this f of v. F of v is what? f1 of v comma f2 of v. That is f1 of v is what? f1 of x minus y comma f2 of x minus y, right? So this is what? This is f1 of x minus f1 of y comma f2 of x minus f2 of y. And now f1 of x is what? f1 of x is my v1 minus, not note that this y is in kernel f. So these imply that f1 of y is 0. So this is v1 minus 0. And f2 of x is what? f2 of x is as it is. f2 of x is f2 of x minus f2 of y is what? f2 of x minus v2. And when I simplify this, I get this v1 comma v2 here, because f2 of x minus f2 of x is gone, minus minus plus. So I get v2 here. So for this v here, I get that f of v is v1 comma v2. Is this okay now? This is completely different than, we use surjectivity of both f1 and f2 over kernel of f1. Is this okay now? Therefore, f is surjective. Therefore, f is an isomorphism. Any doubts here? If not, then we can move to next question. Just a quick question. Two. Yeah, this question. This is this okay? But so far, Uh, so this question I want to do because determine whether the following maps F on K vector space. I'm just doing this because I just wanted to specify that what exactly this f, I mean the way this f are defined, I wanted to clarify this because it looks different than what it is. So this k vector space we are considering of C infinity k is all smooth functions. So this C infinity is called smooth functions. So these are functions which are n times differentiable for any given n in natural numbers. Many times, infinitely many times differentiable. Yeah, infinitely many times differentiable. K valued functions on the interval I in R. Okay, so this differentiability is, wait, is normal differentiability so far into itself RK linear. They are saying into itself RK linear. Okay, does not matter. So first question is f of x is equal to a n x n. So this x n means n times differentiable. This is not polynomial power. A1 x dot. So x dot here means first differentiable, first, I mean the first derivative df by dx kind of thing. And where this a n to a naught comma b are in this C infinity k I fixed. This is fixed and we have to check. So let me just consider this so far. If we have time, then we will do the next. But so far, so what does this mean actually? That they have said that f of x is for, no, that is for x in where? X in C infinity k I. So this is what? All those f from I to k such that they are saying into itself, does not matter, I to R let us take, such that f is smooth. Okay, this is what it means. So when I'm taking this x in C infinity I, this x is actually function from I to R or k, does not matter. It's some function. Okay, so when I write this f of x, this means that it is a1 times this x differentiated by n times plus a1 plus a1x plus b. So for example, if I take f as x from I to R such that this I going to I square, so my x is actually function x square I to I square. So this f of x is again a function. It is function such that a1 I square. So x n here will be, let us start with the left side. So I going to I square. So this is a1 x plus b, and I mean this a1 del by del x. If I take t here, t going to t square, then this is f of x is actually B as it is, B of t it is. This is a1 of t square because B is in C infinity ki. Plus this, here it is a2 I think. And this is an, it does not matter. This is a2 into x dot. So I'm taking differentiation of this. So this is x dot is d by dt of this t square. So this is 2t. So this is 2t plus a3 here means a3 into x double dot. I hope I'm taking the coefficients correctly. This is oh sorry, this is a0 and this is a1. Yeah, so this is just a1 here and this a2 into this x2, that is d square by dt square of t square, that is just 2, we know, right? And then it is a2x plus, now the third derivation of this x3 is just 0. We know del by del t cube of x cube, sorry, t cube, t square is 0. So this is just 0 everything. So this f of x here is actually a2 into 2 plus a1 into 2t plus a naught t square plus b of t. And this is just multiplication. This is again some function in t. So product of those functions. Is this okay? Is it confusing? I mean, it's just notations, the way they are used. So it is not f of x and then we are evaluating this x. We are actually doing this here, like this. So my f is again some function from I to R such that it is taking images from here. I mean, this is I going to, this is t going to a2, 2. So when I write this a2, 2, this a2 is also a function. So this is 2 a2t plus 2t into a1t plus t square into a naught t plus b of t. So this is my function. This f is actually this. And I'm saying this f belongs to C infinity k I. This is my f of x is actually this. Is this okay? Everything is functions here. The image, the domain is also of functions and codomain is also of functions. So f is actually, yeah, f is from C infinity I to C, this not complex C, this C. And I'm choosing a smooth function and I'm claiming that it also lands in smooth function. Is this okay now? And now we have to check whether this is linear map or not. And again, we have to what we say, do all the checking. And that's pretty okay because see, product of smooth functions is smooth functions. So this, when we are writing here, that is still a smooth function. So that's not a problem. So if I have this, so if I take x1 comma x2 in this C infinity ki, then this f of x1 plus x2 will be what? This an x1 plus x2 n plus so on a1 x1 plus x2. I'm just putting dot here or 1 for a naught x1 plus x2 plus b, right? And if I separate them, this is a1. We know that x1 plus x2n is x1n plus x2n. So differentiability is additive. I mean, f of x differentiation of x1, though two functions, is differentiation of those two functions. So therefore, I get this, is equal to x1n plus a1 x2n, so on. Here I get a1 x1 1, or this dot here, plus a1 x2 dot, plus this a0 x1 plus a0 x2, this x2, and plus this b. And if I want to check this f of x1 plus f of x2, this is what? This is a1 x1n plus not a1, an x1n, so on, a1 x1 dot plus a0 x1 plus b. This is my f1 fx1 plus an x2n plus a2 not a2, a1 x2 dot plus a0 x2 plus b. And when I add those, I get an x1n plus an x2n, so on. I get a1 x1 dot plus a1 x2 dot plus this a0 x1 plus a0 x2 plus this 2b I get here. But here I get only b, here I get 2b. So therefore this is not true in general. So when I define my f like this here, this is not linear in general because this addition fails like this. So if at all I want this, so if I'm writing this in different way, if we want f to be a linear map, we must have b to be 0. 0 means b to be 0 means the 0 function in C infinity ki. Okay. So in that case, if that happens, then this becomes 0, and then this becomes 0, and in that case, these two coincide. This is sorry, I'm again made a mistake here. Here I want an. Yeah, that's it. Yeah, so in that case, these two are equal. So if b is 0, then this. So clearly for non-zero b, this is not a linear map. But if b is 0, then f of x1 plus x2 becomes equal to f of x1 plus f of x2. Okay, again I'm pointing that out, that x1 and x2 both are functions, and now we are applying linear map on those functions, and the resultant is again a function. And for the scalar multiplication, now again when I'm taking scalar multiplication, this a what we say this a is again a function. What is it? That whether it is f on k vector space. So this is k valued function. So since it is k valued function, I can take a in k and f is in C infinity I. Sorry. How is it defined? How? Yeah, k here and I. Okay, so this is here, and then f of this ax is what? An ax n up to a1 ax dot plus b. That's it. No, sorry. A naught x, ax plus b. And a into f of, and note that since, yeah, it's okay. Let me just simplify. So differentiation that d by dx of af, we know this is a into df by dx. Let me take t and x here. This is true, right? I mean, this is partial. This is not partial. This is like proper differentiation. This is true. We know this. So we will be using this, and so this a xn will be what? A into xn plus this a into a1 into ax dot plus a1 into ax. This is just product plus b. And when I take this a into f of x, then this is a into an xn. So on a into a1 x dot plus this is a into a naught x. When I'm writing this a naught x, this is not a evaluated as x. Okay, this is a function x itself plus this is bx. But again, everything is coinciding. So if I just write this like taking all the a's outside, this is anyway multiplication happening in k, so or r, whatever your codomain is. This is just multiplication of functions. Just multiply whatever the resultant value of this function, and that's it. So this again is equal. Everything is equal except for this part. B not equal to, so sorry, this is B, A, B. Everything is equal except for this part. This is not equal. So again, this will be equal. So whenever B is non-zero, this B into AB will be non-zero. Was this bad choice of variable? No, I don't think so. So when B is non-zero and when, let me write like this, B in C infinity Ki, this AB will be this, wait, if not, this is not correct. If A not equal to 1, if A is not equal to 1, then this AB will not be equal to B in C infinity Ki. And sorry. And so that's this is creating problem. So this B part, if it is 0, then does not matter whatever. So if B is 0, then for all A in K, this AB will be equal to B, right? Because 0 will be equal to 0 kind of situation. Then for all B in C infinity Ki, we have this. Oh, so therefore again, second condition fails when B is non-zero. Okay, so therefore F is K linear if this B, if B is 0. Otherwise, F is not a K-linear map. Is this okay? Okay, so this is function. So this is everything is function. This is function. This is product of functions. Okay. So like if my f is t going to f of t is t square, g of t is t cube, then this fg is just if g of t is t square into t cube, something like this. So if I consider all these as function, they are just products. This is f of t plus g of t kind of situation. I mean, this I'm referring here, this here, and this is kind. Okay, so I hope this one was okay. I mean, you can check this properly for other examples which are given. I mean, the second example is pretty easy. That x square plus x naught square. That you can check whether it's linear or not. Okay, so I think that's it. Any doubts here? What we did so far? If not, then we can stop. Okay, thank you. So if there are no doubts, everything will be, I mean, I hope the recording is okay because we disconnected in between. Uh, but yeah, thanks.
Thank you.
Yeah, sure.